In cryptography, key size or key length is the size measured in bits of the key used in a cryptographic algorithm. An algorithm's key length is distinct from its original cryptographic security, which is a logarithmic measure of the fastest known computational attack on the algorithm, also measured in bits. The security of an algorithm cannot exceed its key length, but it can be smaller. For example, triple days has a key size of 168 bits but provides at most 112 bits of security, since an attack of complexity 2112 is known. This property of triple des is not a weakness provided 112 bits of security is sufficient for an application. Most symmetric key algorithms in common use are designed to have security equal to their key length. No asymmetric key algorithms with this property are known. Elliptic curve cryptography comes the closest, with an effective security of roughly half its key length. Significance: keys are used to control the operation of a cipher so that only the correct key can convert encrypted text to plain text. Many ciphers are actually based on publicly known algorithms or are open source, and so it is only the difficulty of obtaining the key that determines security of the system. Provided that there is no analytic attack, and assuming that the key is not otherwise available, the widely accepted notion that the security of the system should depend on the key alone has been explicitly formulated by August Kirchhoffs and Claude Shannon. The statements are known as Kirchhoffs' principle and Shannon's maxim respectively. A key should therefore be large enough that a brute force attack is infeasible, i.e., would take too long to execute. Shannon's work on information theory showed that to achieve so-called perfect secrecy, the key length must be at least as large as the message and only used once. In light of this, and the practical difficulty of managing such long keys, modern cryptographic practice has discarded the notion of perfect secrecy as a requirement for encryption, and instead focuses on computational security, under which the computational requirements of breaking an encrypted text must be infeasible for an attacker. Key size and encryption system. Encryption systems are often grouped into families. Common families include symmetric systems and asymmetric systems. They may alternatively be grouped according to the central algorithm used. As each of these is of a different level of cryptographic complexity, it is usual to have different key sizes for the same level of security, depending upon the algorithm used. For example, the security available with a 1024-bit key using asymmetric RSA is considered approximately equal in security to an 80-bit key in a symmetric algorithm. The actual degree of security achieved over time varies, as more computational power and more powerful mathematical analytic methods become available. For this reason, cryptologists tend to look at indicators that an algorithm or key length shows signs of potential vulnerability, to move to longer key sizes or more difficult algorithms. For example, as of May 2007 update, a 1039-bit integer was factored with the special number field sieve using 400 computers over 11 months. The factored number was of a special form. The special number field sieve cannot be used on RSA keys. The computation is roughly equivalent to breaking a 700-bit RSA key. However, this might be an advance warning that 1024-bit RSA used in secure online commerce should be deprecated, since they may become breakable in the near future. Cryptography professor Ian Lenstra observed that, last time, it took 9 years for us to generalize from a special to a non-special, hard-to-factor number, and when asked whether 1024-bit RSA keys are dead, said, "The answer to that question is an unqualified yes." The 2015 logjam attack revealed additional dangers in using Diffie-Hellman key exchange when only one or a few common 1024-bit or smaller prime moduli are in use. This common practice allows large amounts of communications to be compromised at the expense of attacking a small number of primes. Brute force attack. Even if a symmetric cipher is currently unbreakable by exploiting structural weaknesses in its algorithm, it is possible to run through the entire space of keys in what is known as a brute force attack. Since longer symmetric keys require exponentially more work to brute force search, a sufficiently long symmetric key makes this line of attack impractical. With a key of length n bits, there are 2n possible keys. This number grows very rapidly as n increases. The large number of operations required to try all possible 128-bit keys is widely considered out of reach for conventional digital computing techniques for the foreseeable future. However, experts anticipate alternative computing technologies that may have processing power superior to current computer technology. If a suitably sized quantum computer capable of running Grover's algorithm reliably becomes available, it would reduce a 128-bit key down to 64-bit security, roughly a day's equivalent. This is one of the reasons why AES supports a 256-bit key length. See the discussion on the relationship between key lengths and quantum computing attacks at the bottom of this page for more information. Symmetric algorithm key lengths. U.S. government export policy has long restricted the strength of cryptography that can be sent out of the country. For many years the limit was 40 bits. Today, a key length of 40 bits offers little protection against even a casual attacker with a single PC. A predictable and inevitable consequence of governmental restrictions limiting key length. In response, by the year 2000, most of the major U.S. restrictions on the use of strong encryption were relaxed. However, not all regulations have been removed, and encryption registration with the U.S. Bureau of Industry and Security is still required to export mass-market encryption commodities, software and components with encryption exceeding 64 bits. IBM's Lucifer Cipher was selected in 1974 as the base for what would become the data encryption standard. Lucifer's key length was reduced from 128 bits to 56 bits, which the NSA and NIST argued was sufficient. The NSA has major computing resources and a large budget. Some cryptographers, including Whitfield Diffie and Martin Hellman, complained that this made the cipher so weak that NSA computers would be able to break a DES key in a day through brute force parallel computing. The NSA disputed this, claiming brute forcing DES would take them something like 91 years. However, by the late 90s, it became clear that DES could be cracked in a few days' time frame with custom-built hardware such as could be purchased by a large corporation or government. The book Cracking DES tells of the successful attempt in 1998 to break 56-bit DES by a brute force attack mounted by a cyber civil rights group with limited resources, CF DES Cracker. Even before that demonstration, 56 bits was considered insufficient length for symmetric algorithm keys. In 2002, Distributed.net and its volunteers broke a 64-bit RC5 key after several years' effort, using about 70,000 computers. The NSA's skipjack algorithm used in its Forteza program employs 80-bit keys. DES has been replaced in many applications by triple DES, which has 112 bits of security when used 168-bit keys. The advanced encryption standard published in 2001 uses a key sizes of 128 bits, 196 or 256 bits. Many observers consider 128 bits sufficient for the foreseeable future for symmetric algorithms of AES's quality until quantum computers become available. However, as of 2015, the U.S. National Security Agency has issued guidance that it plans to switch to quantum computing-resistant algorithms and now requires 256-bit AES keys for data classified up to top secret. In 2003, the U.S. National Institute for Standards and Technology, NIST, proposed phasing out 80-bit keys by 2015. As of 2005, 80-bit keys were allowed only until 2010. As of 2015, NIST guidance says that the use of keys that provide less than 112 bits of security strength for key agreement is now disallowed. NIST approved symmetric encryption algorithms include 3-key triple DES and AES. Approvals for 2-key triple DES and skipjack have been withdrawn as of 2015. Asymmetric algorithm key lengths. The effectiveness of public key crypto systems depends on the intractability of certain mathematical problems such as integer factorization. These problems are time-consuming to solve, but usually faster than trying all possible keys by brute force. Thus, asymmetric algorithm keys must be longer for equivalent resistance to attack than symmetric algorithm keys. As of 2002, an asymmetric key length of 1024 bits was generally considered the minimum necessary for the RSA encryption algorithm. As of 2003, update, RSA security claims that 1024-bit RSA keys are equivalent in strength to 80-bit symmetric keys. 2048-bit RSA keys to 112-bit symmetric keys and 3072-bit RSA keys to 128-bit symmetric keys. RSA claims that 1024-bit keys are likely to become crackable sometime between 2006 and 2010 and that 2048-bit keys are sufficient until 2030. An RSA key length of 3072 bits should be used if security is required beyond 2030. NIST key management guidelines further suggest that 15,360-bit RSA keys are equivalent in strength to 256-bit symmetric keys. The finite field Diffie-Hellman algorithm has roughly the same key strength as RSA for the same key sizes. The work factor for breaking Diffie-Hellman is based on the discrete logarithm problem, which is related to the integer factorization problem on which RSA's strength is based. Thus, a 3072-bit Diffie-Hellman key has about the same strength as a 3072-bit RSA key. One of the asymmetric algorithm types, elliptic curve cryptography, or ECC, appears to be secure with shorter keys than other asymmetric key algorithms require. NIST guidelines state that ECC keys should be twice the length of equivalent strength symmetric key algorithms. So, for example, a 224-bit ECC key would have roughly the same strength as a 112-bit symmetric key. These estimates assume no major breakthroughs in solving the underlying mathematical problems that ECC is based on. A message encrypted with an elliptic key algorithm using a 109-bit long key has been broken by brute force. The NSA previously specified that elliptic curve public key cryptography using the 256-bit prime modulus elliptic curve as specified in FIPS 186-2 and SHA-256 are appropriate for protecting classified information up to the secret level. Use of the 384-bit prime modulus elliptic curve and SHA-384 are necessary for the protection of top secret information. In 2015, the NSA announced that it plans to transition from elliptic curve cryptography to new algorithms that are resistant to attack by future quantum computers. In the interim, it recommends the larger 384-bit curve for all classified information. Effective quantum computing attacks on key strength. The two best-known quantum computing attacks are based on Shor's algorithm and Grover's algorithm. Of the two, Shor's offers the greater risk to current security systems. Derivatives of Shor's algorithm are widely conjectured to be effective against all mainstream public key algorithms including RSA, Diffie-Hellman and elliptic curve cryptography. According to Professor Giles Brassard, an expert in quantum computing, the time needed to factor an RSA integer is the same order as the time needed to use that same integer as modulus for a single RSA encryption. In other words, it takes no more time to break RSA on a quantum computer than to use it legitimately on a classical computer. The general consensus is that these public key algorithms are insecure at any key size if sufficiently large quantum computers capable of running Shor's algorithm become available. The implication of this attack is that all data encrypted using current standards-based security systems such as the ubiquitous SSL used to protect e-commerce and internet banking and SSH used to protect access to sensitive computing systems is at risk. Encrypted data protected using public key algorithms can be archived and may be broken at a later time. Mainstream symmetric ciphers and collision-resistant hash functions are widely conjectured to offer greater security against known quantum computing attacks. They are widely thought most vulnerable to Grover's algorithm. Bennett, Bernstein, Brassard, and Vazirani proved in 1996 that a brute force key search on a quantum computer cannot be faster than roughly 2n, 2 invocations of the underlying cryptographic algorithm, compared with roughly 2n in the classical case. Thus, in the presence of large quantum computers, an n-bit key can provide at least n, 2 bits of security. Quantum brute force is easily defeated by doubling the key length, which has little extra computational cost in ordinary use. This implies that at least a 256-bit symmetric key is required to achieve 128-bit security rating against a quantum computer. As mentioned above, the NSA announced in 2015 that it plans to transition to quantum-resistant algorithms.